Hello, welcome to all in organic photochemistry. In my today's lecture, I will explain di-pi methane rearrangement reaction, and this is also called as Zimmermann di-pi methane rearrangement reaction. So molecules which is having two pi bonds and that is 1,4 diene, that is two pi bond which are present at 1 and 4 position, they may give the di-pi methane rearrangement reaction. For example, if you take this substrate molecule and two double bonds are present at 1 and 4 position, so this is 1, 2, 3, 4 position, they may give this reaction. And this two double bond that should be separated by one of the sp3 hybridized carbon atom. So either acyclic or some cyclic dienes can also give this di-pi methane rearrangement reaction. Now, so this diene, this is the one of the, we can say, cross conjugated diene, and if we take this diene, that is 1,3 diene, this is linearly conjugated diene, so such molecule will not give di-pi methane rearrangement reaction. So here you will see during the reaction, first 1,4 biradical would be formed and then 1,3 biradical that would be formed. Now some of the features for this reaction, it is given by 1,4 diene, or we can say 1,4 pentadiene, and it may be substituted one. So 1,4 substituted pentadiene, they gives the di-pi methane rearrangement reaction. And here two pi bonds should be separated by one sp3 hybridized carbon. Okay, and during reaction you will see 1,4 pi radical followed by 1,3 biradical. So during reaction 1,4 biradical is formed, then 1,3 biradical that would be formed. Now, so we may take various cases where this central carbon atom or this terminal vinylic carbon atom, it may be substituted or it may not be substituted. So case 1, when central and vinylic carbon atom, vinylic terminal carbon atom are substituted. Okay, so for example, if we have this diene, this is 1,4 diene, and this central carbon atom is substituted. These terminal vinylic carbon atoms are also substituted, and if we irradiate it, then since pi bonds are present, so pi to pi star transition that would takes place. Electron will go from pi bonding molecular orbital to the pi star anti-bonding molecular orbital, and we may write so these are the two radicals. Okay. Now, so this may rearrange, and to give for this rearranges, and we will get so these one radical present at this carbon, and here it may form a cyclic 3-membered ring, and we have now one radical over here, another radical which is present over here. So now suppose I give it number 1, this carbon, 2, this carbon number 3, 4, and this is 5. And now if you will see, then this 3-membered ring, we have a 3-membered cyclic ring, and we may break. So this is a strained one, so it can break either C2C3 or C3C4, that may break. So as this is a symmetrical molecule, I have taken the symmetrical molecule, so any of this C2C3 or C3C4 that may break. So suppose I break C2 and C3. So if I am breaking this one by radical one, so one radical will come at C2 and another at C3. So you will, so what I can write, so I have broken this one. So radical will come at C3 and another radical is coming at this C2, and this C2 and C1, radical at C2 and C1, it may form pi bond, and we have this radical at C5 also. So one of the driving force for this bond breakage, C2C3 bond breakage, we are getting new this tertiary radical. So this tertiary radical which is formed over here. Now we may write the product, this rearranged product. So where these two radicals it may join and we may get a new product. So the product, as we can write, so one of the radical at this position and another radical is present at this position, so it will form a bond and we are getting the product. So this is the case when we have taken this symmetrical molecule. Now if I take unsymmetrical molecule, if I take unsymmetrical 1,4-diene, so if I take here terminal carbon atom is having phenyl and this carbon atom is having methyl group. Now this is our unsymmetrical molecule. This is unsymmetrical molecule. Irradiated pi to pi star transition that will take place, and one of the electron can go from pi bonding molecular orbital to pi star anti-bonding molecular orbital. So now it rearranges, and after rearrangement, so three-membered ring is formed over here. This is three-membered ring and radical 1,4 radical that is formed. 1,4 radical. So this is 1,4 pi radical and followed by 1,3 biradical, and this is 1,3 biradical, 1, 2, 3. So this is 1,3 biradical which is formed. Okay, now three-membered ring, it will break, and either again this, suppose this is C2, this is C3 and this is C4. Either C2, C3 can break or C3, C4 can break. Now suppose I follow the route where route 1 where C2, C3 breaks. So if I write C2, C3 if it breaks, then what I can write here at C3, one of the radical one radical at C2. So this C2 and this one, it may form a double bond, and this is now we have radicals. So driving force again in the formation of this three-membered ring. This is the driving force. Now another route that we may follow, this is route 2. Route 2, if you will see, suppose C3 and C4 breaks. If C3 and C4 breaks, then so one of the radical at this position and another radical which is present. Okay, so here another radical is present at C4. We have radical at C4. So this radical over here and this radical at this position C4 and this two radicals, it will form a bond. So for one time, as you have seen, the new double bond is formed at here, the double bond is formed over here. So we have, this is 1,3 biradical, 1,3 biradical which is formed, and two radicals are present over here. In this case, the two radicals are present at this benzylic carbon atom and this carbon atom. So this is giving you the more stable radical. This is less stable one, and this is less stable. And here the new tertiary radical is which is formed. This is the more stable one. This is more stable one. So this route, that is the good route. So either otherwise we may join this one, and the product that is formed but here what you will get, the product okay. So or we can say this is the minor product, and this would be the major product, which forms via the formation of this more stable radical. Okay, so this is the case one when central and vinylic carbon atoms both are substituted. Now if I take next case when case 2, when only vinylic carbon atom, or we can say when central carbon atom is not substituted, when central carbon atom is not substituted. If you see this one, I have taken a case where this central carbon atom is not substituted one. Okay, this one is the central carbon atom which is not substituted. Now suppose if we have one of the group over here, suppose deuterium I have taken. Now if I irradiate it, then pi to pi star transition again, and so we have pi to pi star transition, one radical and this and another radical, and we have deuterium over here. Now when central carbon atom is not substituted, then in this case one migration of this hydrogen that will take place, migration of hydrogen atom that will take place. So this hydrogen transfer or hydrogen atom transfer, H transfer, that will take place. So this is the case when central carbon atom is not substituted. So one of the hydrogen with its electron will go over here and will form the bond with this radical. And what is the driving force for this? If you will see, this is the new radical which is formed. Here you are getting new radical. This is also secondary radical, and this one is also a secondary radical. Now, so so driving force is the allylic radical. So here you are getting this allylic radical. One of the allylic radical is formed, which is the driving force for this shift. And now what we can see, so we may write the product So in this case, the new product which is formed, this is the new product. Now case 3, if I take case 3, when central carbon atom as well as the vinylic carbon atom are not substituted. The central carbon atom and vinylic carbon atom is not substituted. Okay, so in this case we will get some unstable product that would be formed here. So we get unstable product. So let us take the case. This is the case where central carbon atom as well as the vinylic carbon atoms are not substituted, and if it is irradiated, pi to pi star transition that will take place, and you may write this 1,4 radical which is formed, and now so either this, any of the bond that may break, and what we will get, we get a double bond over here and one radical at this position, okay, and another radical at this position. Now finally we will get here, we will get a vinyl cyclopropane. So we are getting vinyl cyclopropane, and this, as here we are getting the primary radical, this is one of the primary radical, this is the primary radical, so this is quite unstable one. So such type of unstable product we will get in this case. Now let us take some problems. Now suppose if we have one of the cyclic diene. So the case that we took is that were the acyclic diene. Now if I have this cyclic diene, this is a cyclic diene, and suppose this is the molecule. Now if I irradiate it, pi to pi star transition, and first what we should get a 1,4 radical. We should get 1,4 radical is formed, and this 3 membered ring, and one of this bond, this C2C3 or C2C4 that may break, and what we will get, suppose I break this one, and one of the double bond. Sorry. So we have a double bond at this position, and this is the new radical. This is 1,4 biradical followed by 1,3 biradical. So we have one radical over here, and 1, 2, 3. This is 1,3 biradical which is formed, and this radical and this radical, it will form a double bond, and finally the product which we are getting, this is our product. So these 2 radical it may join to give a product. This would be our product. Now another problem, if I take next one, again cyclic, and now if you take this again, we may proceed in the same way. First we will get 1,4 biradical. So this is a 1,4 biradical which is formed, and now this is 1,4 biradical which is formed. Now we have to see whether this is the symmetrical type of molecule. Now this is the unsymmetrical one. So either we may break this C2C3 or C2C4. Either we may these two, either of these 2 bond can be broken down. So the radical which is formed after this ring cleavage, that should be the stable radical. So if I break if I break from here, then in this case, if I break from here, then what you will get? We get a stable radical. So one of the new radical which is formed at this place, another radical, this is the okay. So these two radicals which are formed, okay, at this position, and this here, this is the stable radical that we are getting, stable radical. So we should break the ring from this position, this bond that should be broken down, and we have one of the double bond radical over here, and this radical, it will form a double bond, and finally the product that we may write, this may join the rearranged product that we will obtain. Now if we have a next question, now if we take this one, this is also a case of acyclic diene, and here after this pi to pi star, we may write that is excited pi state. This is our excited state, and now it may give the 1,4 radical, and one radical will come over here, another radical, and the new 3-membered ring that will be formed. Now, so again we have to see whether we should break from this carbon, this bond that should be break, or this one breaks. So if I break this one, then what will happen? This aromaticity of this ring that would be regained. So this aromaticity that regains, and now so I have broken this bond, and so if I break this bond, then we can regenerate this benzene ring, the aromaticity is regained, and so this route that we should follow, and finally we may join this, and product obtained this is the final product that we may write. Okay, so these are some of the examples for dipi methane rearrangement. Hope you are understood. Thank you.